Okay, so let's see, where are we? Yeah, we're down to property 4. Now, this is where things get a little bit abstract because what we're saying is that there's a zero vector. A zero vector exists, and I probably should have an S on the end of exists, such that v plus 0 equals v. Now, I haven't stated this wholly. V would be any vector in R2. And 0 is some vector that we could add to just any old vector in R2, and the result would be that same vector. Okay, the vector to which we added the 0 vector. Well, what would we add to 1, 7 in order to get 1, 7? Now, pretty clearly we'd add the 0, 0 vector, right? Matter of fact, if we add the 0, 0 vector to any vector in R3, it's very clear that since adding 0 to a real number gives us that real number, we're going to get we're going to get the same vector to which we added this one. Okay? Excuse me. So that would be the 0 vector. We first have to prove that this is a vector in R2. Well, it consists of 2 real numbers, so it is. So this vector certainly exists in our vector space. And if we add it to any vector, if we add it to the vector AB, we're going to get the vector AB. And A and B could be any real numbers. So it's pretty easy to write that down. Might not occur to you to write it that way, but we're trying to develop that skill, or that insight. Okay, so if we go to the polynomials, what's the 0 vector, or the 0 element, in the vector space of polynomials, real valued polynomials? Well, what would we add to x squared plus 5x minus 3 to get x squared plus 5x minus 3? Well, the only thing that we could add to that to get that result would be 0, right? So, is just plain old 0 a polynomial? Well, you have to go back to the definition of polynomials, but it is. A polynomial is just a sum of multiples of non-negative integer powers of your variable, of x in this case. Okay? Well, x to the 0 is a non-negative power of x. Okay? So, and it's equal to 1. Okay, so 1 is certainly a non-negative power. 0 times 1 is certainly a multiple of 1 by a real number. 0 is a real number, and it gives us 0. Okay? And we could actually take 0 times, 0x to the 52nd as our 0 vector. It's still just plain 0. So I say that our 0 vector would be the polynomial p of x that's identically equal to 0. It's equal to 0 for every value of x. That is a polynomial because it's a multiple of whatever positive integer power you wish to think of. And that's the definition of a polynomial. So it takes a little bit of work to verify that this is a polynomial. You have to go to the definition of the polynomial and establish it. Now, over 2 by 2 matrices, what do you add to a matrix to get the matrix you added it to? Okay? If I have the matrix A, B, C, D, what would I add to that to get the matrix A, B, C, D? Clearly, I would add the matrix 0, 0, 0, 0. So then you'd have A plus 0 equals A, B plus 0 equals B, etc. So that's going to be our 0 vector for the vector space of 2 by 2 matrices. Okay? Now another property. It's called the inverse property, and I don't know if I even wrote that down. I'll write it here just to write the word. This is the additive inverse property. Now your book, of course, is able to say a lot of things that I could say everything in class. I could read you the book in class, but if I tried to say it all, I'd say it too fast and you wouldn't pick anything up. So I, of course, leave it to you read some things in the book, and that would be one of them. But that's something I could have written down, and I'm sure I probably mentioned it. I'm sure I probably mentioned it. I'm safe in that statement. Okay, so anyhow. Okay, the property is for every u, and u is implicitly a vector in R2, and if you read the full statement of these properties in your textbook, you'll see that they do say it that way. For every u, there exists a vector negative u with a property that u added to negative u gives you the zero vector. Now you see that in looking at a vector space, before you can even talk about additive inverses, you've got to get the additive identity. And it looks like I didn't write that down. I was gone. Okay, this is the additive identity. And this is the additive inverse property. Okay, so additive inverse is what you add to a vector to get the zero vector. And you call that thing you add the negative of the original vector. And that's the additive inverse. And of course, this is the additive inverse of this, as well as this is the additive inverse of this. When you add two vectors to get the zero vector, those vectors are additive inverses of one another. Okay. So, we can write this down, and this is how you begin writing things down. Just let u equal AB. If you don't like AB, you could add aardvark anthill, as long as they're understood to be numbers, real numbers. Then what vector would you add to this vector AB? A and B can be any real numbers. Doesn't matter what they are. If we add to this vector, negative A, negative B, we're going to get 0, 0. So negative A, negative B is the inverse of AB. If you're given a vector and asked to find its inverse, just put negatives. Change the sign of every row in that column vector, okay? So that's the idea of additive inverses, okay? Now, how about over polynomials? Well, if u is equal to the polynomial p of x, and whatever u is in this space, it has to be a polynomial because this is a space of polynomials, right? So u is some polynomial p of x. But what would you add to the p of x polynomial to get 0? You would add the negative of the p of x polynomial. So what polynomial would I add to this first one to get 0? Well, it would be negative x squared minus 5x plus 3. Write that out, simplify it, you're going to get 0. Very simple, but you have to know to think about it. Now, I didn't mention what you would do with matrices. I'll let you think about that. Okay, anyhow, that's your additive inverse property. Okay, another property. If C is a real number, then C times U is in the space. And this is actually another closure property. You're saying that the space is closed under multiplication by real numbers. If you multiply a vector by a real number, you still get a vector in R2. So we can write that out. What do we mean by C times U? Well, let U be the vector AB. X1, X2 if you like, Y1, Y2, Q1, Q, it doesn't matter. Just give these two components names and establish that they're both real numbers. Then when you multiply by the real number C, well, the rule for multiplication tells us that that's C times A and C times B. Now, is this a vector in R2? It is if this is a real number and this is a real number. Well, C is a real number, and if this is a vector in R2, A is a real number, and when you multiply two real numbers, you get a real number, so CA is a real number. And the same argument tells you that CB has to be a real number, provided this is in R2 and this is a real number. Okay? So I say C times this vector is this vector, which is in R2, provided AB is in R2. And I label maybe doubly specified that C is in R. Okay, now what do we do if U is a polynomial? What do we mean by multiplying a polynomial by a real number? Well, clearly, U would be some polynomial P of X, and if we multiply U, which is P of X, by some real number C, well then we're multiplying through the polynomial by a real number. Meaning, we're going to multiply the coefficient of every power of X by a real number. Of course, the coefficient of every power of X is a real number, so when we multiply it by C, which is a real number, we're going to get a real number. So every coefficient of our product is going to be a real number, so we're going to have a polynomial with real coefficients in X. So Cu is a polynomial, etc., real coefficients in X. Now what if we multiply a 2 by 2 matrix by a real number? Well, again, we multiply every element in that matrix by that real number. Every element is a real number, so every product is going to be a real number, so our new matrix is going to be all real numbers. It's going to consist of all real numbers. Okay, now there's another vector space that we kind of went ahead and talked about, and that's the space of continuous functions defined on the interval 0, 1. So we'll pick that up in a minute.